Welcome, AP Calculus. So today I'm going to be providing commentary on how to score the 2018 AP mock exam. So this is the released administration for 2018. We're doing this as our mock exam number 2. All right, here we go. So we're starting off with question number 1, which actually is, I think, by far the hardest problem on this whole entire mock exam. So that sucks that you have to start off with a difficult one, but here we go. So we have a derivative graph, and we want to know how many people enter the line. So that is your very classic integral. Derivative up to a normal function is integral. And this is a calculator problem. So you just plug it in there. Integral, what that means is if you just write this, then you get the first point, and then your answer is 270. This didn't say that you have to write out this sentence for the answer. It just says how many people. So if you just put 270 people, then that's fine. You don't need units. You can just put the number. For part B, this is difficult because it says how many people are in line. That's an integral at a point. So we talked about how integral at a point means initial condition plus integral. The problem is that this problem is very difficult because you have people getting into the line, and then people are exiting the line at a constant rate of 0.7. So you had to subtract those. So if you even considered the minus 0.7, if you even considered it, then you get a point for that, and then you get a point for your answer. That was difficult. This problem is called a work problem. So we're going to see a lot more of these next week or the week after. So for part C, what's the first time that there's no people in the escalator? So after time t equals 300, then you just tack on the number of people that are coming out to make sure that all 80 of those people who are in line get out. So you need to so this is the little equation to do that, and then took 414 seconds. Make sure you're accurate to 3 decimal places. But you'll notice you can round or truncate. They don't care. Part D. So this one, here we go. We have a minimum. Minimum is that T-chart thing, extrema. So we have a T-chart, and if you just consider that critical number, if you even consider that critical number, then you get a 0. So that critical number is right here. Okay, so if you got either of the T1 or the T2, if you just have that anywhere, even if it's not on your T chart, if you at least consider it and you identify the T there, then you get it. So then your answers, we have minimum. We have our answers down there, and then we have 4 people in line, and then you have your justification. And your justification is the T-chart. Your justification is the T-chart. So if you consider endpoints and critical numbers, that is the justification already. It's not really a because statement. Okay, so let's move on to number 2. So that one was really difficult, folks. So we're going to move on to number 2. We have a particle motion problem. We did motion. So particle moves along the x-axis with a velocity. So this is a velocity graph, and we want to find the acceleration at a time. So that's just your very classic do a derivative at a point. This is a calculator problem. You just literally use your calculator. I personally would do this on your main screen. I would do this on your main screen, not your graph, but you could do this on your graph, and you just need the answer for the point. Okay, then find the position at a point. This is your classic IC, your initial condition, plus your integral. So if you just write the integral anywhere, then you will get a point. If you even consider your initial condition, so if you have -5 anywhere, then you are using your initial condition. And then finally, your answer. Wow, we have done problems almost exactly like these. Very exciting. Okay, so we're going to evaluate an integral now. And this is all calculator, okay? So you literally just plug it in a calculator. You know exactly how to do that. So that's your first answer, although you need both answers. Evaluate the absolute value as well. There is an absolute value button in your calculator. It's called like ABS or something like that. So you can do those calculator, and then the interpretation. So the integral, the interpretation for that is net change or displacement. Displacement means net change. Okay, you can use either one. So by the way, it's net change of position. You have to say net change of position. So net change of position is displacement. And then here we go. Absolute value of V, that is total distance travel. You have that in your day 1 study guide. Wow, this is all coming together. So we got part D here. We have a second particle, and at what time are they are the two particles moving with the same velocity? So what you want to do is you want to set the velocity, which is this function, and this is all in your calculator, equal to the derivative of the other particle's position. So if you set the two velocities equal to each other, we got velocity, and then we got the derivative of position, which is also velocity. If you just have this equation anywhere, then you get a point, and then you get a point for just putting in your calculator and finding an answer. You know that on our shortened AP exam this year, it's all non-calc, but these are calc. Okay, so testing your calculator skills. Moving on. All right, so we are moving on to number 3. Oh, here we go. This is exciting because we have a derivative graph, and this is a classic FTC problem where we are accumulating area, and this first problem is asking us, we have an initial condition. We have an initial condition. Oh, I'm on the wrong question here. We have an initial condition, and we want to find the value of an integral at a point. Again, look at this. IC plus integral. Every problem so far has had the fundamental theorem of calculus. It's so fundamental to calculus. All right, so you'll also notice the bounds are out of order. So then we flip that order, so we make that negative. We have an integral. What that means is if you just have this integral written anywhere, you'll get a point. And then your answer, leave it unsimplified. If you went all the way to 25/2, then you're wasting time. All right, so then we just evaluate an integral. Okay, that's fine. So evaluating an integral, so this is non-calc, but we have a function for g now. We have a function for g between 3 and 6. So we have the integral where we have just geometric areas. And right here at 3, we switch from being a square to being a parabola. Okay, we switch from a square to being this g of x function. So they want you to split that up at 3, and that's fine. So we just have the area of a square, which is 4, plus the integral of this whole parabola, which is right here. Antiderivative. What that means is this right here. This is called an antiderivative. It's the answer for when you do an integral, but you haven't necessarily plugged in your numbers yet. So that's what antiderivative means. So if you have that, then you get the second point, and then your answer is 10. All right, part C. On what open intervals is a graph both increasing and concave up? We did problems almost exactly like this. So we got your intervals. We got your answers. So 0 to 1 and 4 to 6, because the derivative, which is g, we even showed our work like that, is positive, and the derivative is increasing. Those are buzzwords that we now have memorized. Yay. Okay. Oh, this is so exciting. So part D, find the x-coordinate for the point of inflection. We did this exact problem too. Decreasing to increasing, aka relative extrema. Those mean the same thing. You could put either. So if you put because the derivative, or g, changes from decreasing to increasing, that's your reason. Or if you put relative extrema, and then certainly your answer is x equals 4. Wow. We did almost this exact same problem in our review lesson so far. This is really cool, folks. We're moving on to number 4. We have a table problem. We are covering table problems in a future lesson, okay? So don't worry if you struggled on this one. So this first one just wants us to estimate a derivative. Estimating a derivative is your classic Algebra 1 slope AROC, okay? So then we have 5 halves there. So that's your estimate. Interpretation is you have to have the rate at which the height is changing. The rate at which the height is changing, because we start with height, and when you do a derivative, that's a rate now. It's a derivative. It's a rate of change. Okay, so rate at which the height is changing. So if you don't have anything that talks about the rate, then you don't get that point. You also don't get the point if you don't get the units right. Meters per year. Meters per year. So if you don't get either of those right, then you lose that whole point. All right, part B. Why? Explain why there must be existence. We just went over existence theorem. Why there must be at least one time for which a derivative is 2. Existence of a derivative is mean value theorem. Okay, we just went over that. Really cool here, folks. All right, so you get a point for just realizing that to start the mean value theorem, you need an AROC. You need an average rate of change. And then conclusion using the mean value theorem. Okay, you need condition. you need the condition. So differentiable and continuous is part of the mean value theorem. And then you need to cite the mean value theorem. So if you have both of those, then that is called using the mean value theorem. All right. Part C is the average height. Okay, so we want to use a trapezoidal sum. So this is really difficult because it's asking you to do a Riemann sum, and trapezoid is the longest one, and it's using it to approximate the average height. So we have height, and we want average height. That means average value, 1 over b minus a. Now, you don't have to have this necessarily written here, but you do have to have that 1 over 8 somewhere in there because average means 1 over b minus a, when it's average of the world that you're currently living in your evidence. All right, so then what does it mean to do a trapezoidal sum? You have to have all of these, you have to have 4 terms where you have sum of the bases b1 plus b2 all over 2 times the function height, right? Function height f. So if you have 4 of those, then you're doing the trapezoidal sum, and you get that point. And then obviously your point for your answer there. Okay, so, and by the way, stop here. Do not go any further with arithmetic, okay? Non-calc, this is a really mean problem. I can't even imagine this is non-calc, but it is. Okay, so part D. Okay, so this is a related rates problem. We have not covered related rates yet, but just as a reminder, related rates is when you have variables that don't agree. G of x, and we're doing that dt. That's the derivative of g times, this is an implicit derivative here. Just like we used to call that y prime. If we have the derivative of the derivative of something, then we tack on a y prime after that. We have the derivative of g, and then we tack on the dx dt after that. Okay, to actually take the derivative, this is a quotient rule. So we have a low d high, high d low, 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 and then again times dx dt. Dx dt was given to you in the problem, that 0.03 right there. Okay, so if you realized that you had to do this little chain rule and chain rule and implicit, where you tack on the y prime afterwards, that means the same thing, really. And so if you did this at all, this step right here, if you did that, then you get both points for those 2 points, and then your answer is 3 over 4. Yeah, this is a pretty difficult problem because you have chain rule / implicit, and it's a quotient rule, and you've got some simplifying to do. I mean, it's a part D. You've got to expect that some of these are going to be pretty meaty. Okay, so we're moving on here. We got okay, this is sort of just a mismatch of fundamentals. We actually did that today. So that, I consider this one of those fundamentals problem because we start off with average rate of change and slope of a tangent line. So for question 5, average rate of change, AROC, that's your very normal algebra 1 slope. We should be getting that at this point. All right, part B, slope of a tangent line. Slope of a tangent line is literally just do a derivative, which does, this is a product. So we got a 1 d2. So we got 1 d2 minus plus 2d1, except the derivative of cosine is negative sign, so that's a minus. So that's 2d1, and then they plugged in 3 pi over 2. Okay, so that's your slope. All right, part C, absolute minimum. We have another absolute extrema problem. So there's actually 2 of these table problems on this administration. Very cool, because now we know what that means. You have to just find the critical numbers, identify those critical numbers as candidates, and that you don't even have to get the final answer yet. You already get 2 out of the 3 points if you just understand that absolute extrema means you need critical numbers. All right, and then so we have endpoints, and then we have critical numbers. Okay, so you need to identify all 4 of those as candidates. Endpoints and critical numbers for absolute extrema. Then your answer with justification. Now remember, your justification is the table and considering your endpoints and critical numbers. And then you just need to choose the number that is the smallest, which is this negative thing. Okay, and you don't need to know how big that is because it's the only negative one. That's how you know it's the minimum. All right, part D. So we have a limit of a quotient. We haven't gone over this yet, but this is our good old friend L'Hopital. So we got L'Hopital. How do we know it's L'Hopital? Because we want a limit with a quotient where when we actually try to evaluate, this function, we get an indeterminate form, 0/0. So you need to show that that quotient is 0/0, 0 divided by 0. So you need to show the condition of L'Hopital's where you have 0/0, which means that this is an indeterminate form. That's applying L'Hopital's rule. So if you figured out that they were both 0 and then you apply L'Hopital's rule, what it means to actually apply L'Hopital's rule is you have to show that the limit of the normal functions equals the limit of the derivatives. We're going to practice that, and you used to be very good at that. So that's called applying L'Hopital's rule. And then your answer is right here. Your answer is right there. Okay, folks. So that's number 5. We got one more to go. This is cool. Okay, so number 6 is a huge differential equations problem, and we got a slope field. So we got a diffie-q here. It wants you to start by sketching out the solution that goes through 0, 2, and 1, 0. So this dot here, you can just visually tell there's a line that goes right through that, so you want to just draw that in. And then this dot here, you want to sort of just follow the curves, follow the current, follow it, and then just it ends up being that. So basically your curves, you would have to have a straight line, and you would have to have something that kind of goes like down like that. So if you have that, like what I just drew in blue, that would probably be good enough. I mean, it has to go through the dot, has to go through that dot. But yeah, but that would be good enough, I would think, for credit still. Okay, so then we got a particular solution. We got a particular, we don't have particular solution yet. We want to do the tangent line. So tangent line means we need a slope, and that's implicit. Just plug in your x equals 1 and y equals 0 into your diffie-q, and that gets you 4/3 when you plug in 1 and 0 for x and y. And then we just put together our point slope equation. The AP test, they always show in y-intercept form, slope-intercept form, but do point slope. You don't want to have to convert that. Oh, and then we have a tangent approximation. We just went over this in day 3. So that's where you plug in that 0.7 in for x, and you just get an approximation. And this one did not ask you to justify if this is an underestimate or an overestimate, but we know that has to do with concavity, concave up or concave down. All right, so then last, we have a monster 5-point diffie-q problem, okay? Just like in the mock exam we did last, every single FRQ administration is always a monster 4 to 5 point diffie-q. So we got to separate those variables first. Just throw the y's over with the y's, throw the x's over with the dx's, and that's called separating. If you don't separate, you are completely screwed. 0 points, nothing. Okay, antiderivatives. That means this step. Once integrals go bye-bye, once the symbol of integration goes bye-bye, that's the antiderivative. Plus C, constant of integration. You have a ceiling for how many points you can get if you don't have a plus C. That's why I have assigned people to be plus C people. You're helping us remember. Plus C, you got to solve for that plus C. Constant of integration, that doesn't mean writing plus C. That means finding the 1/3. Use as initial condition. You just need to even consider this initial condition. X equals 1 and f of 1 is 0. So if you even consider that anywhere, so if you use that f of 1 is 0 anywhere, then you're considering the initial condition. Then solves for y. So y is right here. It says it tells you what the domain is. You don't need to have that for full points because it's obvious that functions are only defined on their domain. All right. So, wow, this was very exciting because we're actually starting to see quite a lot of content that we have already doubly reviewed in our review sessions. I hope you found this helpful. I will be posting the cutoffs for how you can score yourself. So, get started with your scoring if you haven't done that already. Good luck. Let me know if you have any